Hello and welcome. Today what we're going to do is spend a few minutes talking about descriptive statistics. Fundamentally in statistics there are two types. There are two types of statistical approaches. One is called descriptive and the other is called inferential. Now, today we're going to talk about descriptive, but just to be clear of the differences, descriptive statistics are all about looking at a sample or a group of individuals, in our case, or a collection of data, whereas inferential is the way in which we take a sample to give us an indication of the total population effect. So we will talk about this in a separate video later. Today we are going to talk about samples and descriptive statistics. And all of us have probably well experienced with what sample descriptive statistics are about. The important thing is that these are, just to give you an indication, what sorts of things are we talking about? We're talking about means, medians, modes, standard deviation and variance, those sorts of statistical outcomes that we often see written up in papers and in newspapers and things. So that's the sorts of things we're going to talk about today. But obviously a really important thing about a sample is that in the end what we're going to do with a sample is try and translate across to giving us some indication of population. And to do that, we need to be sure about how the sample was selected. And in a later video we will talk about the process of selecting a sample that makes it representative of the population. Now, to give you the obvious example here, if I took myself, my brother and my sister and determined the number of decayed teeth in us and said that that's what the total population of Australia was, you'd all just sit there and laugh at the idea of that. There is a bunch of factors in my selection of that sample, me, my brother and my sister, that tells you immediately that that cannot be representative of a population. So clearly selecting a sample is a very, very important part of using statistics in appropriate ways. But that's for a later discussion. Let's move on now and talk about means, medians, modes, standard deviations, and this collection of elements called descriptive statistics. I will spend 1 or 2 minutes just running through them just to remind you of how they're calculated, so you can have a clear understanding of them. Let's talk about the average or the mean for a moment. It equals the mean. And the way you often see that written in statistics is an X with a bar on top of it, the mean. And you all know what the mean is. If we write down a series of sample numbers, making it a bit tricky for myself here, all we do is we sum these numbers up. So we got 1 plus 2 is 3, 6, 10, 14, 19, 25. So we have 25, and we divide it by the number of samples. 1, 2, 3, 4, 5, 6, 7. And that equals 7 threes are 21, so it's 3 point something. And I'm not going to bother calculating it out, but you can see that that's how you calculate a mean. And that's okay in many situations. But if I was to say, what would the mean of, say, 1, 2, 2, 734 be? You'd suddenly see that the mean would be a number, sort of, call it 740 divided by 1, 2, 3, 4, let's say. It's about 740 divided by 4, which would make it, call it 150 plus. as a number, which when you look at this sample, you would immediately say, look, that's not, that a mean doesn't actually give you a good central tendency representation of this sample. So that's where mean is good, but it has risks in it as well. So the other types of methods, we all know about what a median is, so we'll just run through a median for a minute. Just draw a line across there, call this a median. A median is if we have a series of numbers like this, 1, 2, 3, 4, 4, 5, 6. How many numbers do we have? 1, 2, 3, 4, 5, 6, 7. So the middle number is the somewhere between the third and the fourth number in. 1, 2, 3. That is the median. So the median equals 4. And this is a much better thing for that little problem we saw above. I've forgotten what those numbers were. What were they again? 1, 2, 2 and 734. So if we had 1, 2, 2 and 734, what's the median of that? Well, we've got 1, 2, 3, 4 numbers. So the midpoint, and this shows you another little trick with a median, the midpoint is halfway between these two. So what you do is you take the mean of that, so you go 2 plus 2, and you take the midpoint of that, divided by 2, and so therefore it is 2. Remember, this 2 represents the n. I'll just put an n down there to remind you. So you just take the midpoint. So the median in this case is 2. Which would make a much better feel for you about this sample. Basically, a median sort of eliminates these outriders way over out in beyond the normal range of what you're expecting to see. So that's a median. We keep rolling down. Let's talk for a moment about what a mode is. Let's just draw a line there. So we've done median. Let's draw a mode now. What is mode? A mode is another way of describing the central tendency of a sample. So if we have 1, 2, 3, 4, 4, 5, 6, what is the mode of this? Well, that's really easy. The mode is where you see the same number repeated the most number of times, and in here you can see there is just one number repeated. So the mode, in this case, equals 4. And that's just another way of representing a central tendency. In colloquial terms, I'd call it the most common element in this collection of data. So they're the simple 4 central tendencies. I'll just write that word out because that explains something for you. Please, these are designed central tendency. These methodologies are designed, if you've got a collection of data, to bring you towards some representative center point of the data set. So a central tendency calculation, average, median, mean, mode, doesn't tell you anything about the distribution or the spread of your elements along the collection of data that you have. It only tells you what is towards the middle of this sample. So if we want to talk about something that gives us an indication of what it gives us distribution, they are some separate sorts of calculations. So moving on from talking about central tendency, we now want to talk about how we measure dispersion in a sample. So in other words, dispersion is a way of describing how spread out a sample is. Is the sample a narrow, tight sample like this, or is the sample a long, spread out sample with various values through that sample? So you can see that the two things together, the central tendency of a sample and the dispersion of a sample are critical to understanding a sample, to describing a sample. So if we just look at this for a minute, the most commonly used description of dispersion is called the range. Now the range just is the lowest value and the highest value, the lowest value and the highest value. So in this case, if we said this was, let's call this 6, let's call that 1, let's call that, say 20, and let's call that 100, we could say the two ranges, one sample has a range of 6 to 20, and the other sample has a range of 1 to 100. And that would tell us the spread of this sample in very simple form. However, you can be tricked by this because because remember, you have a central tendency in this as well. We might say the central tendency point is here and the central tendency point is sort of here, depending on how you're measuring it. So range is one way of describing the dispersion, but probably not the one that we see most commonly in scientific literature. That's more sort of for newspapers and things. The one we see most commonly in the research literature is the standard deviation. I'm not going to write that out, I'm just going to write standard deviation. And standard deviation, in very simple, loose language, is really sort of a distance, the distance that each sample, let's call this sample 1, the distance it is away from the overall mean of the sample. And you just measure all of those distances, and you accumulate those distances up in a mathematical form. So the standard deviation produces you, let's draw a few more here, let's imagine that sample 2 is here, and that's the distance 2, and basically the standard deviation at the end of the day is some arrangement of all the d is related to the distance each sample is away from the central tendency or the mean of the sample. There's a whole bunch of mathematical ways that this is, well, there is a mathematical approach to calculating this, and please do have a look in a book and actually learn for yourself how that is calculated. I'm going to write here, look this up, and remind yourself of the process by which the standard deviation is calculated. There is a similar term, or there's a similar approach taken that produces a similar outcome, and that is called the variance. Which is highly related to standard deviation. In fact, the variance is more used by statisticians than it is by sort of users of statistics like clinicians, etc. And the variance is actually based on the square factor, and therefore it's a number that tells you dispersion, but it's only lightly comparable back to the sample numbers because of this squaring factor in it. So if you just sit down and read a variance number, it doesn't actually, you can't rapidly grab that and build yourself a picture of the distribution of the sample because of the square factor involved. So variance is something that's used more by mathematicians and statisticians, whereas for us mere mortals in the world, we're more of a standard deviation, because from that number you can actually infer rapidly the distribution of a sample. So to complete this story, I just want to give you a few tips on what does standard deviation mean to us. And there's some really simple things that you can actually remember as very basic statistical readings of papers. When you commonly read a paper, what you will see is the mean plus or minus the standard deviation. Now let's just put some numbers down. Let's imagine this is 3.6 plus or minus 1.2. And what does that mean? Well, what we can tell you, very simply, in rule of thumb terms, that tells you that if you took the value 3.6 subtract 1.2 and you used that at one end of a line, and at the other end of the line you used 3.6 plus 1.2, you could tell that about 68% of your sample will have values between those 2 points. So in other words, this is the mean subtract 1 standard deviation up to the mean plus 1 standard deviation covers about 68%, or just a little over 2/3 of the sample. And to extend that, if you have the mean minus 2 times the standard deviation through to the mean, let's get that right, plus 2 times the standard deviation, that distance covers about 95% of your sample values. And just to be complete, if it was plus or minus 3 standard deviations, that will cover about 99% of your sample values. So that's some neat handy tips when you're reading papers. If you see a value like 3.6 plus or minus 1.2, you know that, let's just quickly work this out, 2.6, 2.4, 2.4, and 3.6, 4.6, 4.8. Between the values 2.4 and 4.8, about 2/3 or 68% of your 68% of the values that this sample found sit in that range. So that's a neat little trick for understanding means and standard deviations very simply. Now this is not a surprise, and I'll just write that out again. 1 standard deviation is 68, 2 standard deviations is 95, 3 standard deviations is 99. These are not by random mathematical chance that these are like this. There's actually a reason for this, and that reason is based on something that we'll talk about when we talk about probability in a little while. The reason that this arrangement is like this is because of that normal distribution curve that is supposed to be symmetric, but my drawing isn't so good. So this is actually based on that normal distribution process, and we can calculate these in high precision because of this curve. But we'll come to that in a later date. So to summarise, where have we got to today? What we've talked about is descriptive statistics. And descriptive statistics apply just to a sample. And they are usually, we get 2 sets of outcomes from that data. Either we get a central tendency and we can get a dispersion. And the sorts of things that we use to describe a central tendency are things like mean, median, mode, and I've missed one, mean, median, mode, and others. I can't remember, but you can look back at them. And in the dispersion, we can use range, which is more a newspaper sort of thing, when it's not really something we use in statistics, standard deviation, and variance. Remembering that the key ones for us as researching clinicians, and the most common thing that we'll see, is standard deviation and mean. Do remember, mean does have some risks in it. We talked about that. Let's just remind ourselves. The risk in mean is about its distribution. remember what we said, 1, 2, 3, 3, 734, I think, from memory. Remember that if you calculate the mean of that, it was actually quite unrepresentative of what the sample really meant. So you have to be a wee bit careful with all of these statistics that the underpinning statistical assumptions hold firm in their calculations. So that's where we're going to finish the theoretical component of the talk today. What I want to do now is give you a couple of examples using Excel of how these calculations are done. Now, well aware that there are high-powered statistical packages that we all want to jump in and use, like SPSS or GenStat, all these statistical packages. However, I'd highly recommend that at the very beginning you start with very simple, well, literally I'd start with a pad and a pencil if you've never done any of this before. But if not, I would get Excel open and just actually do the calculations once or twice for yourself by hand, because that way you'll actually understand what goes on in the calculations that are done automatically in statistical packages. In addition, you can sit there and experiment a little bit and look at some of the crazy outcomes you can get when you don't follow the basic core assumptions underpinning these calculations. So here we are, we've got a little bit of Excel open now, and we're going to have a little experiment in actually doing some of these descriptive statistics. So first of all, I'm going to put ourselves a little sample of data in here, and I'm just going to make some numbers up. So let's go 12, 23, 45, 15, 7, 19, 34, 11, 21 and 9. So now it's really easy to see here we've actually got 10 elements in there, but and I'd highly recommend you actually learnt how to use the very basic formula structure of Excel to do calculations yourself. So the first thing we'll do is let's do a count to see what the n is. So we just put the formula in equals count and we highlight those cells like that, and it will tell us we have 10. Now let's do the average, so we can just see what an average looks like. Equals, and Excel has a formula for this, average, if you can spell right, there we go. Highlight the cells you want to take the average of, close the parenthesis, done. So the average is 19.6. So that's fine. We can also get out the standard deviation. Standard deviation, whoops, those we need to start with an equal sign. Standard deviation. Highlight the cells so we can see what that is. There we are. We've plonked it in the wrong place, so we'll just put it over here. Standard deviation. Standard, we'll try a hyphen this time, deviation, and let's just do the variance, remembering the variance is a statistical tool that we use to make calculations. So I think it's variance. Variance. If we can spell variance, I-A-N-C-E. No, maybe it's just var. Yes, it's var. So we can calculate the variance quite simply. However, that doesn't give us a feel of how those formulas, standard deviation and variance, are actually calculated. So I thought what we might do is actually calculate a standard deviation by hand and actually see what we do, see what happens. So the first thing is, what we need to do is we may need to find out the difference from the mean. And that's really simple to do. If we know the mean is 19.6, we've calculated it over here, 19.6. So if we know that difference, we can just go equals the value, subtract 19.6. We'll try that formula, equals the value, subtract, try again, 19.6. And there we go. So we just extend that to all of them. and you can see that calculation there now. And then if we take the square of that, which is the next thing that we do, we'll just put a little line here so we can see this is the number. Then this is going to be the difference from the mean, and this is the difference squared equals the square of that. There we go, the square of it, and we put that in. So we can start to see we're building up the structure of this. And then it's rather simple. The first thing to do is what is the sum of the squares. So we need to calculate what the sum of the squares is, which is quite simple. We just calculate the sum of this equals the sum of this. Here we are, like that, which is 1290. And then to calculate the variance, so we'll just put that, we'll call that the sum of the squares. The variance is equal to the sum of the squares divided by the number, which is the count of this, which we know is 10, subtract 1. So the variance is 143.377. So I think the important thing to read from this is that the variance is actually looking at, in its core meaning, is the distance of each value away from the mean. So you can see how that was calculated. Now it's adjusted for the sign and it's done a few other things. And just to finish this calculation off, to show you how you get the standard deviation, the standard deviation is the square root of the variance, 11.97. There we go, we can show that that is equal to our formula-driven 11.97. So what I want you to see here is that the standard deviation rests upon the calculation of the variance, and the calculation of the variance rests upon the difference of the value from the mean. Now, if we wanted to experiment now, because we've done this all with formulas, we can just change some of these values and see what happens. Let's imagine that one number becomes a hugely crazy number. And the first thing to notice is you can see the average has gone up dramatically, but at the same time the standard deviation has gone up dramatically. So when you read this, it immediately tells you that there is a significant spread of these numbers. In fact, let's do another one. Let's make this one something crazy as well. Again, now you can see the standard deviation has become even larger against the mean. So what a standard deviation tells you as a clinician when you read a paper is how spread out are these numbers, is your sample value set. We'll just go back to the original numbers now so you can see that it ends up with a relatively small standard deviation. And if you run your eye down the original numbers here, you can see that it is a relatively small standard deviation. It's a relatively tight spread. So if we did the reverse thing, let's imagine that 45, look, it's the outstanding one, it's the one way higher than the others. If we took that back to something in the middle here, 23, look how far the standard deviation has now dropped. It's dropped by it's dropped by 10. So you can see that by bringing things back towards the middle, should we try another one? What if we brought 31 back towards the middle? If we made that 34 back towards the middle, if we made that 24, see that? The standard deviation has shrunk even more as you move the sample back towards its middle point. So I think by doing these sorts of calculations by hand, it actually shows you how the high-tech statistical packages do it, and you can sit and experiment for a while in Excel to look at what those effects are on these statistical packages. What that really means for you as clinicians is when you look at a raw set of data, you'll actually be able to use your eye and to look at it and go, okay, I can see that that will have quite a high standard deviation, or the mean will be about here, or you'll be able to rapidly assess the data that's flowing in. Now that might be useful in research terms, but even more importantly, in your clinical activity, it will make you look at data in a very different way. As you look at the flow of numbers of any type that come along towards you, you will look towards mean and standard deviation to tell you about the sample that you're looking at. And in general life, it makes you a far more rigorous reader of data that you read in the paper about, say, election predictions and those sorts of things. I note recently that in the leading newspapers and things in Australia, not only now do you see the predicted poll outcomes for elections, but you are starting to hear the relative error risk in the numbers that are presented, which is just another sort of colloquial way for the public of talking about standard deviation and things. So you will start to use these sorts of distribution factors in your assessment of all sorts of data in your life. Thank you.